Welcome to AERO 1020 Theory of Flight, presentation number 4 on the Pitot-Static System. The Pitot-Static System provides airspeed, altitude, rate of climb, or rate of descent information. It provides pressure information to the following instruments: the altimeter, the vertical speed indicator, and the airspeed indicator. This slide shows what is commonly known as a standard six-pack of flight instruments. These are analog round dial instruments that you commonly see in older aircraft. The Pitot-Static System instruments are the airspeed indicator, the vertical speed indicator, and the altimeter. Static pressure is the pressure of still air. And we learned in the last presentation that static pressure actually decreases as we climb in the atmosphere, and static pressure acts equally in all directions. The static port on the aircraft is designed to capture the pressure of still air outside of the aircraft. The pitot-static system in the aircraft consists of the static port or static ports, the pitot tube or tubes, and all of the associated lines and connectors running from the static ports and the pitot tube to the pitot-static instruments in the aircraft. The pitot-static system in this diagram shows the pitot tube mounted under the left wing and labeled as number 1, and the line from the pitot tube runs to the airspeed indicator. The static ports are labeled as number 2, and the lines from the static ports run to all 3 of the pitot-static system instruments. So the pitot tube only feeds information to the airspeed indicator. So remember that the airspeed indicator is the only pitot-static instrument that gets information from the pitot tube. All 3 of the pitot-static instruments receive information from the static ports. The static ports are usually mounted on the side of the aircraft where the air is relatively still, flush with the fuselage. They also may be mounted behind the pitot tube on some aircraft. The static ports provide the static air pressure or the pressure of still air to the altimeter, the vertical speed indicator, and the airspeed indicator. An alternate static source is usually located inside the cockpit in case the external static ports become blocked. It's important to remember that if you are using the alternate static source, the pressure will be less than the pressure outside the cockpit due to the Venturi effect. Because the static port provides information to all 3 pitot-static instruments, it's very important to check the static ports before every flight during your pre-flight inspection to make sure that the static ports are not blocked. The pitot tube is usually located on the leading edge or beneath the left wing, away from any turbulence. It provides total air pressure to the airspeed indicator. It may be heated to prevent ice blockage. Here's a picture of a pitot tube mounted underneath the left wing of an aircraft. The altimeter measures altitude using static pressure from the static port. The altimeter is a device used to measure a height above a given level based on the static air pressure or the pressure of still air or ambient air. There's an aneroid wafer inside of the instrument casing that can expand and contract in reaction to changes in the static pressure inside the instrument casing. Aneroid means not wet or mechanical. Remember, the aneroid wafer is sealed. Air cannot escape or air cannot go into the aneroid wafer. And it has the ability to expand and contract. There are usually several of these aneroid wafers stacked on top of each other. As an aircraft climbs, the ambient pressure, the static pressure, decreases, which allows the aneroid wafers to expand. The aneroid wafers are attached to some levers and gears which drive the dial on the face of the instrument. to show the indicated altitude. This figure shows the inside of the altimeter with the aneroid wafer that can expand and contract, and it also shows the face of the instrument. And it's important, if you are using an analog altimeter, to know what each hand represents. In this illustration, you can see that the short hand represents thousands of feet, and the long hand represents hundreds of feet. The long thin pointer represents 10,000s of feet. So in this illustration, this altimeter is indicating the aircraft is at 3,700 feet. The altimeter is calibrated using ISA, or the International Standard Atmosphere. ISA, again, is an internationally agreed upon atmospheric distribution of temperature, pressure, and density. And each altitude above mean sea level has a prescribed pressure. Movement of the aneroid wafer in response to the pressure inside of the instrument will indicate the altitude given for that pressure in the International Standard Atmosphere when the altimeter is set for standard conditions at 29.92 inches of mercury. This figure shows two different aircraft with two different settings in the pressure window on their altimeters. The aircraft on the left has a pressure of 29.92 set in the pressure window, which is also known as the Colesman window. Because it has the standard pressure of 29.92 set in the Colesman window, the altimeter reads the height above the standard pressure, or the standard datum, of 29.92 inches of mercury. The aircraft on the right has the local altimeter setting of 30.10 set in the Colesman window. And because of that, the altimeter shows the height above sea level, because the local altimeter is the pressure at sea level. This figure shows an aircraft sitting on the ramp at an airport that is 360 feet above sea level. The aircraft has the local altimeter setting of 30.10 inches of mercury set in the Colesman window. Because of that, the altimeter reads the height above sea level, because 3010 is the pressure, the current local pressure at sea level. This figure illustrates why it's so important to reset your altimeter with the local altimeter setting when you're flying from one area to another, especially if there's been a pressure change. If you fly from a high pressure area to a low pressure area without resetting your altimeter, then your indicated altitude shown on your altimeter will be higher than your true altitude. So your aircraft is going to be lower than you think. The same thing happens with temperature. If you fly from an area of high temperature to low temperature, then your altimeter is going to indicate that you're higher than you really are. Your indicated altitude is going to be higher than your true altitude. If your static port is ever blocked, for example with ice, the pressure inside of the static port will not change. It'll stay constant. So your altimeter will show a constant altitude, even if you're climbing or descending. Again, it's important to know how to read the analog instrument if you're using one. Remember, each pointer represents something different. The long, thick pointer represents hundreds of feet. The short, thick pointer represents thousands of feet. And the long, very narrow pointer represents 10,000s of feet. So you can see this is below 1, so this aircraft is below 10,000 feet. And this is right around 4,000, and this is around 700. So the altimeter is indicating 4,700 feet. Although it's important to remember that if it is 4,700 feet, then this short, thick pointer would be past the 4. The Diamond DA-40 is a technically advanced aircraft with an electronic flight information system. It also has an electronic flight display. This is a picture of the primary flight display, or the PFD, in the cockpit of the Diamond DA40. And as you can see, instead of a round dial presentation of instruments, it has a digital presentation. The altimeter, showing the altitude of the aircraft, is on the right side of the primary flight display, and it's a digital presentation instead of the analog presentation. The next pitot-static instrument is the vertical speed indicator. The vertical speed indicator is a device used to measure the rate of climb or descent. It consists of a case that receives static pressure through a restricted passage, also known as a calibrated leak. There's a diaphragm inside the casing of the instrument that receives unrestricted static pressure. Here's another look at the inside of the VSI. As the aircraft climbs or descends, the pressure decreases or increases, and the diaphragm senses the change in pressure immediately. But the casing does not sense the pressure change immediately because of the restricted passage. So the expansion or the contraction of the diaphragm is delayed due to the delay in the change of pressure inside of the casing. And that's transmitted through the linkages and gears to indicate either a climb or a descent. When the pressure in the casing of the instrument equalizes with the pressure inside of the diaphragm, the dial then returns to 0. Here's another look at the vertical speed indicator. You can see the diaphragm inside of the casing and the calibrated leak. And you can see in this figure that the vertical speed indicator is indicating a climb of about 1,200 feet per minute. Here's a look at the primary flight display on the Diamond DA40. You can see that the vertical speed indicator is on the right hand side of the altimeter, and as the vertical speed changes, this tape changes to show the rate of climb or the rate of descent. Now the last pitot-static instrument to discuss is the airspeed indicator. The airspeed indicator is a device that indicates the speed that the aircraft is moving through the air. It consists of a diaphragm within a sealed case. One side of the diaphragm is exposed to static pressure, while the other side is exposed to total pressure. Total pressure equals static pressure plus dynamic pressure. Static pressure is pressure of still air, and dynamic pressure is the pressure of moving air. Dynamic pressure is the pressure caused by the aircraft moving through the air and impacting a surface. And while the aircraft is not moving, dynamic air equals 0. Therefore, static pressure equals total pressure. Dynamic pressure increases with the movement of the aircraft through the air. Total pressure becomes greater than static pressure, causing that diaphragm to move. And that movement is transmitted through the linkages and gears in the instrument to indicate an airspeed. So remember, when the aircraft is standing still, inside of the Pitot tube, you only have static pressure. Dynamic pressure is 0 at that point, so the static pressure in the diaphragm is equal to the static pressure in the casing of the instrument. Once the aircraft starts to move, then dynamic pressure is added to the static pressure inside of the diaphragm to get total pressure. And that total pressure compared to the static pressure in the instrument casing is then transmitted through linkages to indicate an airspeed on the face of the airspeed indicator. Here's the face of an analog round dial airspeed indicator, and notice that it's color-coded. Each colored arc on the airspeed indicator represents a different operating range. For example, the white arc represents flap operating range. Those are the airspeeds you want to maintain with your flaps extended. The green arc represents normal operating range, and the yellow arc is your caution range. You only want to maintain those airspeeds in smooth air. The red line represents the never exceed speed, or VNE. That's the maximum speed for all operations. Exceeding VNE could result in structural damage. At the bottom of the white arc, or in other words, at the lowest airspeed on the white arc, you have VSO. VSO is the stalling speed in the landing configuration. In other words, your landing gear is down, your flaps are lowered. At the bottom of the green arc, or in other words, at the lowest airspeed on the green arc, you have VS1. VS1 is the stall speed with the landing gear up, flaps up. In other words, that's the stall speed in the clean configuration. At the top of the white arc, in other words, at the highest speed on the white arc, you have VFE, which is flap extension speed. That's the highest speed you want to maintain with your flaps extended. And then at the top of the green arc, or at the highest airspeed on the green arc, you have VNO, which is normal operations maximum structural cruising speed. On the primary flight display in the Diamond DA40, the airspeed is indicated on the left-hand side in a digital format. And you can see it is color-coded just like the analog instrument. Here's a link to a video about the Pitot-Static System and Pitot-Static instruments. You can watch it if you have time. It's optional, but I highly recommend it if you want a more in-depth understanding of the Pitot-Static System and the Pitot-Static instruments. That's the end of the presentation on the Pitot-Static System and Pitot-Static instruments. The next presentation will be on different airspeeds and different altitudes.